Okay. Is it working?
Yeah.
Oh, okay.
It's fine.
Well, I might just put my computer next to it so I can look at notes or so I can at least see my slides.
All right, we'll get started today. Our speaker is Matthew Berens. He's a PhD student working in WRS under Bill Arnold. And he has a bachelor's degree, as I understand it, from Bethel University
Yes, I do.
Chemistry and
Biochemistry, yep.
And today he's going to talk to us about his PhD research. So we're very pleased to have you come. Thank you very much.
Yeah, thank you for having me today. Like you said, my name is Matt Berens. I'm in the Department of Civil, Environmental, and Geoengineering. I work in the lab of Bill Arnold. He's our primary advisor, co-advised a little bit by Paul Capel as well. Most of my research there focuses on the fate and transport of organic pollutants in natural waters and sediments and groundwater. But today what I'm going to focus on is some work that I've been doing over the last 3 years looking at the transformation of nitroaromatic compounds, specifically nitro-containing munitions compounds, and how they're degraded by redox reactions that occur on iron-bearing minerals, and then ways that we can effectively monitor those reactions, and then better ways to evaluate remediation successes at contaminated sites. And so what I have here, this is actually a picture of the Twin Cities Army Ammunition Plant up in Shoreview, about 5 miles up the road, that I'll be talking about a little bit today in my talk. But so I've titled the Monitoring, Enhancement, and Prediction of Subsurface Pollutant Transformation by Iron-Bearing Minerals, and a stable isotope approach, so to quantify reactions on the iron-bearing minerals of pollutant transformation. I'm going to focus on stable isotopes that are present for the quantification. So I'm going to start out by talking about why, well, if this computer, I don't think it's hooked up to the computer at all.
Use the arrows or the page down.
No, I mean, the mouse working? Oh, there it goes. Okay. So I'm going to start off by talking about why would we want to study environmental stable isotopes and how they're applicable for the field of pollutant remediation. So stable isotopes have many uses in the applied environmental sciences. For one, they're used a lot for things like understanding trophic interactions. They're very useful in tracing energy flow from producers to higher order consumers. You can track nitrogen and carbon isotope values in food sources and look at enrichment as you move up the food chain. You can track elements through various environmental compartments, processes such as the nitrogen cycle, plant-to-animal metabolisms, elemental transport. Isotopes are also extensively used as tracers in hydrologic studies to characterize flow paths, residence time, aging, distributions, things like that. But how I'm going to be using it is in reaction monitoring. And so when you use stable isotopes in reaction monitoring, you measure the ratio of heavy to light isotopes in a compound as a function of the concentration of your pollutant over time as a contaminant is degraded. And what you find is that as a contaminant decreases in concentration, it tends to become more enriched in a heavy isotope throughout the reaction progress. And so as we track these ratios as a compound is transformed, it allows us to diminish a lot of ambiguous interpretations that might happen when you typically monitor pollutant concentrations. When you see actual changes in isotope ratios of compounds, it's a way to tell if a contaminant is actually being degraded. Whereas if you just go out into the field and take measurements of a pollutant over time, you might notice decreasing concentrations from things like sorption to sediments or volatilization or dilution, but you're not actually remediating a pollutant of concern. Something else that is useful with the stable isotopes is it also allows you to distinguish chemical manufacturers as well. And so down here on this plot, I have a range of, you might see an enrichment in the isotope ratio of a compound over time as your pollutant concentration decreases. But every contaminant or every chemical compound that's made has a distinct chemical isotopic signature that varies from manufacturer to manufacturer. And so that's ways that stakeholders can prove or provide evidence at a contaminated site that a certain compound is coming from a certain source or a certain manufacturer, etc. So our work targets insensitive munitions. These are a new class of energetic materials that are aimed at increasing safety during production, handling, and disposal. So currently a lot of compounds used by the military are things like TNT or RDX are some of the more well-known ones. However, they're getting replaced by some of these other compounds such as DNAN or NTO or nitroguanidine. And they're often present in these mixtures like this. So IMX 104, PAX 48, and IMX 101 are three munitions formulations that are currently in use by the government and the military. And so while these new compounds that are being phased in over the last several years are much safer for storage, handling, disposal, they're inherently, because they have a lower sensitivity than some of the traditional ammunitions compounds, they become more prone to incomplete detonations and scattering of fragments over land and soil and water. For what we know about traditional munitions and nitroaromatic compounds, the recent emergence of these new compounds presents a risk to contamination of soils, waters, sediments, as well as toxicity to a variety of organisms. And I'm focusing today primarily on this compound DNAN, 2,4-dinitroanisole, which is similar in structure to TNT, trinitrotoluene, and it shares a lot of similar chemical characteristics as well. So under reducing conditions in the environment, iron-2 that's associated with iron-bearing minerals is a very efficient reductant of many pollutants and many oxidized contaminants. In this process, you have iron-2 that is either sorbed to a mineral surface or is present structurally within the mineral. And this iron-2 is able to donate electrons to oxidized contaminants such as nitroaromatic compounds and react and form them and generate the reduced form of the contaminant. This is a very efficient process because in the environment, once you have iron-2 that donates an electron to reduce a contaminant, that iron-3 that forms can then be regenerated either microbially or from dissolved iron-2 that is present in the environment. And so what we want to know is, how can we accurately quantify pollutant degradation given the complexity of environmental systems and specifically targeting these abiotic pathways? And then here's the reduction scheme for the compound I'm focusing on, dinitroanisole, where the nitro groups become reduced to these aniline groups during the transfer of electrons from iron 2 on a mineral surface. So to more accurately characterize that process, we leverage naturally occurring stable nitrogen isotope ratios within this compound DNAN. DNAN has 2 nitrogen atoms, which means there's 2 spots where nitrogen 14, which is a naturally more abundant isotope, can be replaced with the heavy isotope nitrogen 15. And then we track the pollutant concentration over time as it's being degraded, and we monitor the stable isotope ratio at the same time. And so as DNAN is decreased, as the concentration becomes less over time, what we find is the ratio of the heavy isotope versus the light isotope becomes higher. In other words, it's more enriched in the nitrogen 15, the less abundant isotope, than the more commonly occurring nitrogen 14 isotope. This is because nitrogen 15 tends to form slightly stronger bonds than nitrogen 14 in a chemical compound, and thus the small fraction of DNAN molecules in the environment or in your sample that contain that nitrogen 15 are degraded much less preferentially and therefore are accumulating in your unreacted pool of contaminant. On the top, I have the general equation shown for what is defined as the delta 15N, or the isotope signature for nitrogen. It's just a ratio of the heavy isotope to the light isotope in your sample. Here we're considering DNAN, compared to an internationally accepted reference standard. For nitrogen, it's just nitrogen that's present in the air. So the reference percentage for 15 nitrogen to 14 nitrogen in the air is about 0.3% or so. Another way to visualize this process is by flipping this plot on its side and looking at the normalized concentration during a reaction process versus the isotope signature. And so in this case, this point here refers to the very beginning of a degradation reaction, and then the 0 refers to once all of your contaminant has been degraded. And putting these values together, you can fit this curve either via a log linear transformation, or you can fit it using nonlinear fitting methods. And you can tease out this epsilon term, which is called the isotope enrichment factor. And it's just a measurement of how much your pollutant or your compound has been enriched in the heavier isotope as a function of that reaction process. And this, these epsilon values that you get from this kind of nonlinear fitting of a plot are specific to each type of reaction pathway, and they're a nice way to account for the underlying mechanism that is occurring, especially if that element is involved in the bond breaking or formation during the elementary reaction steps. And so that allows us to specifically look at the nitrogen in these compounds and tell if the compound itself has been transformed versus just decreasing in concentration from non-degradative processes. So let's think about how we can apply stable isotopes in the field. There are 3 general steps for using this process in the environment. The first thing we do is we do controlled laboratory experiments. This is to understand the concentration and isotope dynamics of a pollutant as it becomes degraded, and calculate the associated epsilon values like I mentioned on the last slide. After that, we can go out into the field and take measurements of isotope signatures. And then from those values, we can generate predictive models that we can apply to isotopes measured in the field to estimate pollutant transformation at a contaminated field site. So going back to our reduction scheme for DNAN, we wondered what parameters we can vary that might affect isotope fractionation so we can better understand this process and provide some insight into how robust this process is, how robust the isotope process is for predicting pollutant degradation in complex environmental systems, specifically related to these abiotic redox reactions that are occurring on iron-bearing minerals. So we looked at 4 general categories of parameters that we might be able to vary. The first, we looked at different minerals. We looked at the presence of natural organic matter. We looked at multiple DNAN exposures. So this is repetitively exposing an iron-bearing mineral or some subsurface environment to a contaminant. And then we also evaluated a few remediation strategies. In terms of the mineral identity, we focused primarily on iron oxides. So goethite, magnetite, and hematite are iron oxide minerals. Macanoite is an iron sulfide mineral. And then we also used 2 naturally collected sediments in soils. One is from the Twin Cities Army Ammunition Plant, the TCAP site. Twin Cities Army Ammunition Plant sediment is rich in magnetite as its primary iron phase. And the Tinker Air Force Base from Oklahoma City, Oklahoma is rich in hematite. In terms of natural organic matter, we explored the effects of alluvial soil humic acid on the reactivity and the isotope profiles during this process. We took our systems and we exposed them to multiple contaminant spikes, looking at 1, 3, and 5 sequential spikes of DNAN to the same system. And then remediation strategies. We used something called in situ chemical redox manipulation, or in situ chemical reduction. And to do this, you apply a reducing agent to a natural system, whether it's directly into a monitoring well. In our case, we added them to columns and various experimental reactors. And the goal of in situ chemical reduction is that it generates iron 2 on the mineral surfaces that then can act as electron donors, because in many environments, the iron that is present is non-reactive and doesn't have reduced forms present. So these are plots showing various different minerals that we used for DNAN reduction. And what we found when we exposed DNAN to our goethite, magnetite, and macanoite minerals is that reaction kinetics varied minimally within each mineral system as a function of multiple contaminant spikes and natural organic matter. So this first panel is showing how DNAN degraded in the presence of goethite with aqueous iron 2 present, and the second one is showing magnetite. These are very similar in the fact that whether we were just adding DNAN once, as in the spike 1, or if we added it several times in a row, or if we added allyl humic acid, the first order rate constants didn't really change. The only difference that we saw was with macanoite, which is an iron sulfide mineral. We did see that as we repeatedly exposed the mineral to DNAN and repeated these reactions more than once, the rate constants did slow down and the reactions progressed less preferentially over time. The difference with macanoite is that macanoite is a structural iron 2 mineral, whereas goethite and magnetite are iron 3 minerals. And so with goethite and magnetite, we have to continually resupply our reactors with iron 2 so that we can maintain reactivity within the system, whereas in macanoite, we're relying on structural iron 2 to degrade the pollutants. And so as you continually expose a mineral to DNAN or macanoid to DNAN, in this case, the iron 2 becomes depleted in the mineral, and you see some loss in reactivity. So I'll also add that mineral identity, pH, and buffer has shown to affect the quantity and distribution of products, which are not shown here. Here we're just focused on the parent DNAN molecule. We also looked at DNAN reduction by natural materials, both on their own and after in situ chemical reduction. So this left panel is showing the reduction of DNAN by TCAP sediment, and then what I call the TCAP extract. As I mentioned earlier, TCAP is the TCAP sediment. The reactive iron mineral is magnetite, and so in the TCAP sediment, all that's present is magnetite and sand, essentially. And so to look at the primary reactive portion of the TCAP sediment, we took a magnet and extracted out the magnetic portion, referred to that as the TCAP extract, and then compared it to pure magnetite. And so in this case, the solid lines are referring to reactors in which we took sediment materials and exposed them to iron 2 and conducted batch reactions where we spiked in a known amount of our DNAN compound and watched it degrade over time. The dotted lines refer to reactors that received in situ chemical reduction or our remediation strategy. In these cases, we found that the reactivity did plateau over time, which indicates that the amount of reactivity that's generated in a sediment or a soil it needs to be replenished with multiple amendments of a reductant. On the right-hand panel, these are the same reactions, but they were done with the soil from the Tinker Air Force Base and hematite. I had these paired together. As I mentioned, the primary iron phase in Tinker Air Force Base soil is hematite, and so we compared them side to side. Much like the TCAP sediment, the Tinker Air Force Base soil is composed almost exclusively of hematite and sand. When we measured the isotope profiles over time during these reactions, we found that the isotope fractionation is not affected, either as a function of multiple contaminant spikes, the mineral identity, or the presence of our Elliott soil humic acid. And what we find is that the 15N, or our heavy nitrogen, becomes significantly enriched in our DNAN molecule as the reaction progresses, whereas we also measured carbon as well. This is the ratio of carbon 13 to carbon 12, and we found that there was little change, if any, that occurred during the degradation process in carbon. And this tells us that the reaction is occurring at the nitrogen atoms, specifically that nitrogen atoms are involved in the formation or breaking of bonds during the rate limiting step, whereas carbon atoms are left unaffected. The right-hand side is just the same thing, but it's shown for our natural materials. And this is indicative of abiotic reduction. And so if we were seeing a different transformation process, for example, if we were monitoring a reaction of DNAN reduction or oxidation mediated microbially, we might see reactions that are occurring more at carbon centers instead of nitrogen atoms, in which case we would see significant trends of enrichment in carbon 13 over time instead of nitrogen. But what this isotope fractionation profile allows for us to do is to discern that the type of reaction pathway is abiotic reduction, specifically at those nitro moieties like I showed in the beginning figure. Okay. So once we have to perform those laboratory experiments, we've characterized that process, we can calculate an isotope enrichment factor, that epsilon value, based on the plots that I showed on the last page. Then the next step is to actually go out and measure isotope signatures in the field or in the lab, in our case, to begin with, to validate what we have found so far. So first, we began by doing some mock field studies. We did this using a single blind approach with sediment columns. To do these experiments, we took glass columns and packed them with sediment materials from either the Twin Cities Army Ammunition Plant or the Tinker Air Force Base. We then exposed these columns to our in situ chemical redox, our in situ chemical reduction remediation strategy, in which we pass sodium dithionite through the column to generate reactive iron 2 on the soil surfaces before we expose the columns to our oxidized pollutant DNAN. What we did then was we measured the remaining pollutant concentration coming out of the column at all points during our reaction. And then we also sent a subset of the samples out to measure the isotope ratios. What we did not do is we did not tell our collaborators who measure our isotope values what the concentrations were. And in this case, we were hoping to use this as somewhat of a single blind study to see how well we could predict the extent of transformation, or how well our collaborators could predict the extent of transformation giving just the isotope values that they were measuring and the isotope enrichment factors that they calculated previously. Using the isotope enrichment factor, that epsilon value that I showed previously, we can generate conceptual diagrams like this, where this delta 15N value down here is the deviation in the isotope signature from the unreacted compound. And so for DNAN, or as I mentioned before, the typical reference value for nitrogen in the environment is about 0.3% nitrogen 15. However, for our DNAN molecule, we find that to be about negative 2.4 per mil, or negative 0.2%. And so any deviation from that is measured along the x-axis here. And then the y-axis is showing the extent of reaction. And so, for example, if our collaborators measure an isotope signature in our DNAN molecule that is 20% higher than our unreacted compound, we can draw a line up on our conceptual diagram and say, well, we're likely predicting an extent of reaction that falls somewhere around 70 to 75%. And so, as I just mentioned, we can use those values to measure or to estimate the extent of transformation at a contaminated site. When we put all this together, we end up getting a workflow that looks something like this. So this is what we did this is basically a summary of the entire process. First, we did controlled laboratory experiments where we measured the normalized concentration during the degradation process and the isotope signatures that occurred at the same time. What we then did is we fit all of those data points together to generate one isotope enrichment factor for everything. We're able to do this because all of our data points were so consistent with respect to the mineral that was used, with respect to the presence of natural organic matter or multiple contaminant spikes. And we found this one value of negative 15 plus or minus 0.6, which this value agrees very closely with almost all other values that are used for nitroaromatic compound reduction. We can then generate these conceptual models linking the extent of isotope enrichment during a reaction process to the extent of reaction, wherein we can measure the isotope signature during the process and then estimate our extent of reaction from a plot, from isotope values that might be measured in the field. What we found when we used this to predict actual extents of transformation from field samples was our model fit very well. So on the right-hand side, I have some preliminary results from when we predicted the concentrations versus the actual values. And so this is a linear regression of our predicted values from our model versus our actual values that we measured in the field. And we found that the data fit very nicely. The slope here was 1, plus or minus 0.1, with a mean absolute error of 0.09 as C over C naught, or as a normalized concentration value. There was some tendency to underestimate the extent of transformation at the lower values, which ultimately is not a bad thing. And it's also very typical in the environment as well. So you can get a lot of preferential flow paths in the environment based on differences in soil characteristics and heterogeneities, which can take your contaminants to transport via one of many flow paths, which might each induce different degrees of transformation over time. However, when we got to further extents of transformation, we did notice that these data points tended to align pretty well with one another. And so ultimately, why is this important? So first off, there's very limited data available about using compound-specific isotope analysis to monitor the degradation of insensitive munitions. And this is specifically going to be of importance as these new munitions compounds are becoming phased in over time and replacing some of the more traditional compounds. So far, we've been able to show that we can use this isotope analysis as a tool to monitor the degradation of insensitive munitions. And I added in here that we can also evaluate the extent of biodegradation that occurs as well. As I mentioned previously, we see significant nitrogen enrichment in our compound, which is indicative of abiotic reduction. But if we were to see microbial degradation or non-reductive pathways, we might see reactions that are occurring at the carbon molecules instead of the nitrogen. And so when we plot nitrogen versus carbon isotopes against one another, we can generate two-dimensional plots that look like this. And so the red data are all the data from my experiments that I showed previously. And in this case, nitrogen fractionation, or the amount that nitrogen becomes enriched, is shown on the y-axis. And the corresponding value for carbon is shown on the x-axis. And so, as expected, there's a large amount of nitrogen enrichment happening with very little carbon. But when we look at biodegradation or alkaline hydrolysis, which are primarily oxidative pathways, we see less nitrogen fractionation and more carbon fractionation. And in this way, you can measure the isotope signatures throughout a reaction process and make assumptions and interpretations about what pathway is controlling the degradation of your compound of interest. And so far, most of the work that has been done for munitions compounds, and specifically these insensitive munitions like DNAN, have been all focused on biodegradation and oxidative mechanisms. And so what we have been able to do is provide one of the first assessments looking at abiotic pathways. We can quantitatively estimate munitions degradation despite varying matrix conditions and remediation strategies. This is a very important thing to note because field sites tend to be very complex. They tend to have very different hydrology, mineralogy, underlying solution chemistry, soil chemistry, things that might cause reactions to progress at different rates and to different extents. And being able to show that while concentration measurements might vary over time as a function of any one of these field parameters, the isotope fractionation profiles do not. And as I already mentioned, our work emphasizes abiotic processes where traditionally much of the research focusing on munitions degradations has been with biodegradation or oxidative pathways such as alkaline hydrolysis. And ultimately, this work can be used to improve natural attenuation protocols. Things like monitored natural attenuation are kind of one of the gold standards, essentially, or in a sense, for monitoring pollutants in the field, because you can use things like isotope analysis to prove to stakeholders that your site is remediated to a safe enough extent without having to go in and do invasive remediation strategies like pump and treat, or scooping out extensive amounts of contaminated soils and sediments, or installing treatment wells. You can save a lot of money and avoid a lot of unnecessary perturbations to the environment. So this data right here is all shown for our synthetic minerals that I talked about at the beginning: the goethite, magnetite, hematite, macronite, those pure iron oxide-bearing minerals. But this process was also repeated, including our natural materials. And so in this case, the red triangles are referring back to those pure goethite, magnetite minerals, and the stars are showing our natural materials as well. And so whether we're using pure iron oxides in the laboratory, or we're degrading these compounds using naturally collected materials from the field, the isotope fractionation profiles all tend to look like one another, indicating, again, the robust nature of this process to predict pollutant transformation in the field from these isotope enrichment factors. So from that, I'd like to thank some of our collaborators, Bill and other lab members, Jen Strela, who did a lot of work with us, who postdoc when I started. And then our collaborators in this project are at AEVOG, the Swiss Federal Institute of Aquatic Science and Technology, specifically Thomas Hofstetter, Bridget Ulrich, who's now at NRRI, and Koff, who did and is currently doing much of our isotope analysis work on the analytical side. And this work was funded through the CERTIP grant, a subsidiary of the Department of Defense. So I can take any questions related to the work.
Can you tell us a little bit about what DNAN is degrading into after it goes through this process that you talked about?
Yeah.
What are the byproducts?
So when it's reduced like this by iron minerals, it's primarily reduced to this diamino form. And so it doesn't typically go beyond this if it's just abiotic processes that are reducing it. But if you can couple the biotic and the abiotic processes together, you can get it to mineralize a lot more you can actually get ring cleavage, and you can get smaller carbon compounds that might break off during microbial metabolisms, whether it's CO2, whether it's formaldehyde, or things like that. Just in terms of abiotic reduction, like we were concerned with, this is as far as it goes here.
Is that product considerably safer than the parent? Or?
Unfortunately, it's not. Fortunately, it's not considerably safer, and it does have a slightly higher aqueous solubility than a slightly higher tendency to absorb the sediments than the parent compound does. But in the environment where these are coupled, this is strictly in an anoxic environment where this reaction can happen. In natural environments where you're getting fluctuations in redox conditions from higher or lower oxygen content and the presence of both biotic and abiotic processes, it does get degraded then into more innocuous forms.
So are the soils always below the water table for this type of thing to happen?
For reduction to occur, they would, yes. They would need to have some sort of persistent anoxic conditions. Otherwise, the iron 2 that you have would just precipitate out as iron 3. And that's one of the needs for the remediation strategies, like the in situ chemical reduction using things like dithionite, or other agencies use polysulfides or zero valent iron or things like that, is that in conditions where you have fluctuating water tables or fluctuating redox conditions, you don't always have iron 2 that can persist on the mineral surface, because as you change that electrochemical potential or the redox profile, it's going to precipitate out as iron 3 and it's going to become non-reactive. So adding in those remediation strategies like dithionite, like we did, we can generate these reduced forms of iron, which are then reactive to degrade the contaminants, even in situations where you might not have persistent anoxia. And the dithionite is a pretty attractive remediation strategy in the sense that you can add it to an aquifer or your injection well, your monitoring well, and it reacts very quickly with the iron in your sediments or your soils to generate these reactive iron 2 species. However, dithionite itself is not very long-lived. It degrades through aqueous, it degrades in aqueous media very quickly to sulfite, and can further be reduced or oxidized as such.
The kinetics for the degradation in the lab, which were very fast, anywhere 4 to 16 hours, are those representative of the kinetics that occur in the field?
Yeah, yep. So we observed, so some of the rate constants that we saw using our field sites were, so the TCAP sediment was over an order of, within about, so this one right here, the solid darker blue line is sediment collected directly from the TCAP site. And so we were seeing degradation there in about 2 days or so, but these have relatively high iron concentrations, iron 2 concentrations versus what you might see in the field. So you would expect it to be a little bit slower. And much of the work that has been done in the field is focused on microbial degradation opposed to abiotic processes. But it's becoming increasingly important, especially at sites like TCAP, where it was thought for a long time that all of the chlorinated solvents and other compounds that have contaminated it for long periods of time were being degraded biotically. But recent work in the last 10 years or so has shown that it has been these biotic processes, or the abiotic processes, that have been controlling it. But I would say that yes, this tends to be representative of what we would see in the field in terms of a rate constant. Dissipation times tend to be fairly quick. And it's also hard to tell too, because you do get mixtures of abiotic and biotic processes that are occurring at the same time. And so that'll affect your rate constants. And our isotope fractionation profiles, we can make interpretations about to what extent biotic is contributing and abiotic is contributing. But those coupled together will have an influence on the rate constant as well, which tends to be very site to site. Yep.
How far out does the injection, you're injecting this into the well? So you create a plume this when you downgrade it?
Of what we're injecting?
Yeah.
Yeah, so it would theoretically create some sort of plume that's moving downstream, but it does react so quickly with the iron minerals that it's almost all oxidized right away to sulfur bearing, mostly sulfate.
But how do you detect how much or I should say transport
Of the pollutant?
Yeah, so you need to know what the distribution of that is, and I suppose we get that from some monitoring wells that, they're saying go to map and stuff like that.
Yeah, and so you might, so you'd inject your remediation compound at one well, and then you can monitor the isotopes or the concentration of your pollutant at further downstream wells. And so you are assuming that you do have some pollutant of your contaminant. And that's one of the reasons why we're using the isotope profiles here, is that the concentration profiles tend to get very complicated when you are adding in your remediation compounds, because you're introducing various disturbances to the system, which might affect pollutant concentrations, but don't actually induce any pollutant transformation. Yeah.
How many sample replicates do you have
For this, these are all done in triplicates. And the isotope studies tend to be done in a lot more samples. So each of these points has triplicates, analytical triplicates. So each of these points are measured multiple times on the instrument. And then when we perform these experiments, our isotope, to perform the isotope analysis, we need a lot more sample than just measuring the concentration. And so we actually have one reactor going for every time point during a reaction. So instead of having, to do one pollutant degradation reaction, instead of having one reactor that you sample, various times, do it in triplicates, but then you have one reactor for every single time point. And so it's at least triplicates.
And since it depends on the iron concentration,
Yes.
naturally, if there would be more iron soil with these conditions in it,
Not necessarily, no. So in order for these reactions to occur, there does have to be some amount of dissolved iron too on the surface. And so there are other metals that can mediate these processes. Iron 2 tends to be the most reactive. But in the environment, there does tend to be enough iron 2 present, either just from a dissolved pool in deep anoxic environments, or from microbial metabolisms. There tends to be a lot of iron-reducing microbes that can make a living off of this, generating iron 2.
this is part of active DoD efforts for remediation.
Yes.
All right, well, thank you very much.
Yeah, small group.
Yeah, I think you're towards the end of the semester.
Are we?
Not yet.
That's just, it's like,
Middle of, hope it's not yet.